Hey, John here. Let's talk about move semantics. All right, there's a little bit of terminology involved here as well. Now let's make sure we all understand what I mean when I say aggregation, and that's just a $2 word that says, look, I have a class here, and inside that class I can have other things. Right, these things in here, just integers right now, and a pointer to an array, right? These are, this is an aggregate. Foo is an aggregation of these three, in fact, four, because we have a count down here as well, of these four things. And, there's no reason I couldn't put anything else in here. I could put things like, if I had, I wanted to, I could put strings in here, right? And so on. And I could put pointers to strings. That's all that word really means. Now, when it comes to move semantics, what we're really getting at here, so let's take a look at where we're going, and then we'll conclude and summarize at the end here. Where we're going is we're focused on this pointer right here. There are situations when I have an object like this foo object, whatever it might be, and I want to provide an assignment operator. And I want to assign, foo x and a foo y. I want to say x equals y, right? Well, in those cases, I need to make a copy of this. We talked about that when we were talking about deep copies in our copy constructor. In fact, we got the code right down here. I started out with this is a copy of the last version of the code in the video on copy constructors, okay? And I made a few modifications, all right? And I fixed a bug. We'll talk about that in a minute. The copy constructor, as you recall, is called to say, hey, I need to construct a new foo, and I need that new foo to have the same value of the old foo. So the foo is an aggregate of these parts, right? And therefore, I got to reach into the thing I'm making a copy of and grab out the A and the B, and I need to say, okay, replicate the number and the elements in that array. Now let's take a quick look at set P where I made a mistake. Now in the previous video this was not at all necessary because I never called set P more than one time on the foo object. All right, but that's no excuse. This is just terrible practice. I forgot to put this in there. It's absolutely paramount that if you're going to throw something away and replace it with something new, that you make sure you clean up your old stuff, okay? This is what we call a memory leak. If you forget to delete the old one before you allocate a new one and set this P pointer to the thing that's newly allocated, once that's done, there's nothing that has kept track of where the old one is, and there's nothing to clean it up. So it's my responsibility to clean up the old one first if I'm going to use this method, and I'm going to in this discussion. So it's absolutely critical that we review this and fill in this accidental omission from my previous use of this object. So what do I do here? I delete the array that P is pointing to, and then I say, well, if the new thing, if I say set P, let's say I had a foo object that had an array with 50 elements in it or something like that, and then I call set P on that object, and I want to say here, I now want to set it to have 0 objects. Okay, well, if that's the case, I need to delete the old ones, and if the new value is 0, I don't want to go and allocate and copy anymore. I want to just simply say, okay, remember I deleted it, set P to a null pointer, and remember there's supposed to be 0, and I'm done, okay? If n is not 0, then I would want to allocate an array, and I want to remember how many there are, and I want to copy the array, just like we talked about before, okay? So there's this oops on this omission over here, and we'll see that we need that when we talk about our operators that I've added to this thing, all right? So for all intents and purposes, I've corrected a bug, and now I'm going to add this operator down here. I'm going to add an addition operator. And I have an overloaded assignment operator down here as well. Let's look at the assignment first. To me, the assignment operator has always been a lot like the copy constructor, all right? And that's kind of what this is based on. And so what goes on in here? Remember that the assignment operator has to be a member, and the object upon which it is called is the thing that's on the left-hand side of the assignment. So this variable is the left-hand side, and the reference here is the object instance that's on the right-hand side of the assignment operator. So I print out, hey, I'm in my assignment operator, and I'm going to print out the address this, and I'm going to print out the address of the object on the right-hand side so I can keep track of what's going on. You saw this going on in my overloaded operator lecture before. I need to make sure that I'm not assigning any object the value of itself. And this is important this time. Now, I mentioned this before. This is you basically see this all the time in an assignment operator, because obviously it's a waste of time to assign yourself your own values. In this case, you'll see this is an important thing because it really won't work correctly otherwise. And the short of it is this won't work correctly down here at all if you actually try to assign the value of your P array to yourself, okay? So what do I do down here? I make a copy of the A and the B, and I'm going to make a copy of this P array, and this is where we run into that situation where the bug I just talked about would rear itself if I didn't add that logic, because if I ever assign a value to an object that already has a P array, it would have lost track of it, okay? So that's why that bug needs to be fixed. In particular for this example, all right? And it should be done all the time anyway. The fact that it didn't need to be done in the last example was just no excuse, all right? That was a big mistake. All right, moving on. This is your average assignment operator, no problem. Let's take a closer look at the sum so we understand what it's doing. I print out a big header, and I print the address of the thing on the left-hand side, and I print the address of the thing on the right-hand side over here, right? I dump out the contents of the left-hand side and the right-hand side before I do the addition, just to make sure that we see what the heck is being added. What do? I create this result object. So far, this is basically the same as we saw before. I've got what? I've got my A is the sum of the left and right operands of the plus operator. My B is the sum of the left and right values, right, of the operands of the addition. And I've arbitrarily chosen to define what it means to add two foo objects together by simply, like I said, adding the A's and the B's, and then I'm going to combine the P's. So what do I do down there? I'm going to say if the P array on the left-hand side has, 4 elements, the P array on the right-hand side of the plus operator has 2 elements. I'm going to create a combination of all, the union of both of them, okay, by creating an array that has all 6 of them in there. So what am I going to do here? I'm going to say, well, if both of these things have zeros, right, but no elements at all, then num_p would be 0, and I don't want to do all this copying. I'll just leave it alone. And because the default constructor for the foo object, as you recall up here, sets the num_p to 0, I know num_p is 0, so I don't have to mess with it. In that case, we're already done. On the other hand, if there are any elements at all in either the left or right-hand side, I want to make copies and put them all together in one big, unified array. So what do I do down here? I'm going to say, all right, in my new result object, I'm going to set P to point to a newly allocated array that's big enough to hold all the elements of both of them. Okay, and then I'm going to go through a couple of loops. And this loop here copies all the elements from the thing on the left, and then it copies all the elements from the thing on the right. If you look closely in here, I've got 2 counters going, and I purposely named them J and K so that visually you don't confuse the variables here with I and J, which otherwise might look similarly. All right, so look what's going on here. I set J to 0, and all the results I assign based on the J. So the J counts up forever. I never reset it. K, on the other hand, goes from 0 to however many elements there are that I'm copying out of the source. All right, so these are all the ones on the left, from 0 to however many there are on the left. And here's all the elements from the array on the right, from 0 to however many there are on the right. That's what's in the K. And if you've never seen the notation over here before in a for loop, you can put commas in here and do more than one thing. So it says, start K at 0 while K is less than P. And when you're at the bottom of the loop, add 1 to K and add 1 to J. All right, I do the same thing down here. That's why J And the point here is that J counts up continuously, so don't get confused if you haven't seen that before. When I'm done, I dump out the result. And I print a little message that says, okay, I'm done now with the addition operator, and another big asterisk. So we can see this thing. It just jumps out. Really obvious when we run the program. All right, we already looked at the assignment operator. We know how that works. Let's review what we did down here in the main in our old code. I made a minor adjustment, and I added some stuff down here. So what do we got here? We create an F1, and we set the A and B values. You recall that the parameterized constructor has a variable, has parameters for the A and B values if we want to set them when we construct it, okay? So I create one, and I dump it out, and that one has no P array set to it yet, and we'll see that in the output. I then have an array, and I say, oh, set the P array of that F1 object to the elements of A, and it has 6 elements in there. Clearly, that's 6 elements, okay? And we then dump it out. This time, a little bit different than the last time, I'm going to create an F2 object. I'm going to use the default constructor. It just sets everything to 0, and there's no P array in that case, right? And I'll dump it out, and we'll see that that is, in fact, true. I'm then going to use my newly crafted assignment operator. And I'm going to say F2 equals F1, and then I'm going to print it out. And we'll see that F2 does, in fact, have the same value of F1, and that all the copy stuff that we just looked at up here will work correctly. In other words, it'll have the same A and B values, and there will be a copy of the array of all the P values in there. After that, I'm going to create an F3, and I'm going to set the A and B values to 3, and I'm going to get rid of this extra semicolon. That's not really an error, but it's not clean, so sorry about that. I'm going to then create a B array that has 3 elements in there, and I'm going to set the P array for F3 to this 3-element array, and I'm going to dump that back out, okay? Then I'm going to come down here, and I'm going to do my addition. I'm going to say F1 equals F2 plus F3. We've already seen overloaded addition. I want you to just see what happens when this particular addition is done, so we understand what it means to add these two foo objects with the combined and concatenated array. All right. Then I print, I'm done with my addition now, and I dump out F1 so we can see that the addition had worked. Let's compile it up and run it and see what's happening here. Let's go back up to the top here. Okay, so we run it. Here's where we create the foo. Remember, I sent it to the, give it 2 initialization values here, the 9.9 and the 8.8. And I never set the P array, so it prints it out. There's no elements, and it's empty. I then set the P array, and I dumped it out again. Remember, I set it to the 6 elements of this array. 1, 2, 3, 4, 5, 6, and it remembered, oh, yeah, I got to remember there's 6 of them in there, okay? And I'm printing out the address of the object every time I dump it out. I print the address of where the array is, where these values are, that it's stored in the object, right? So that I could make deep copies and stuff. Remember, this is the example from the deep copy lecture we had earlier. Now, I create an F2 object using the default constructor here, right? And you can see that the address where that is created is the same as here, and that's when I say, oh, this is where the F2 is, and I dump it out. It's a default constructor, so everything is 0 in there, all right? Now I call my assignment operator, which we talked about before, and we just walked through, so it should be no shock to see that F2, it now has the same values in all these fields as F1 has. But as we pointed out when talking about deep copies, when we made copy constructions with deep copies, look at the address of where the P array is in F2. While that has the same value of the elements in the array, this address down here that ends in 52E0 is definitely not the same as the array in F1, which is 52C0. All right? This is absolutely important to keep track of these things, okay? I now create my F3 object. Oops, that's being done right here, and it creates it and it initializes it F2 4D0, which you can see that same address here. It says, here's my F3, and in this time I just created it and I set the P value. I didn't dump it out twice like I did for F2. So here it is after I've assigned the array value, and you can see that the P array for F3 is at this address down here. Okay, we now do the plus operator, and you can clearly see the asterisks and all the dumping here. These are all the output from my overloaded addition. Now let's see what's going on here. I print out left-hand side, right-hand side, and the result when we're done. Okay, so what's all this about? The left-hand side here, we're overloading the addition, so that's going to be the address of the object that's on the left of the plus. Remember, the line of code that's responsible for this is F1 equals F2 plus F3, so we should see that the left-hand side, this address here, should be that of F2. So the thing that ends in F2 4B0 up here is, in fact, F2. Okay, that's good. The thing on the right-hand side is at this address, F2 4D0, and that clearly is the F3. So far, so good. We can also see the values all make perfect sense. The F1 values there, and this is obviously the F3 values, and that all makes sense. Now, as all good overloaded plus operators do, it creates an object so that it can return the sum by value. This is the result variable being created, all right? And then I print it out after I do my math, right? So the A, 102 is the sum of 3 and 99. That makes sense. This 91 over here is the result of the sum of 3 and 88. That makes sense. You can see this array here has all the elements from F1, 1, 2, 3, 4, 5, 6, followed by all the elements of F2, which is the 987. The size is right. Total elements in here is 9. The address of this array is unique and different than the address of the arrays in these other two objects because they're different values. They're just different arrays, right? Now, let's look and see what happens when this sum is consumed. That's the whole point of this. What happens when a method or a function returns an object by value. And this is an incredibly common case when that will happen, okay? So let's say I added together these two things, and remember, these objects have these internal pointers. So in order to make copies of them, we have to make deep copies. There's kind of a lot going on in there, all right? What happens down here now when I do my assignment operator? Well, it dutifully does what it's supposed to do. Remember, this assignment is assigning F1 the value of this sum that is expressed in this temporary object that's created by the overloaded plus operator, and so that it can be returned by value, okay? So look at the address of the right-hand side of the equals, right? The assignment operator. It ends in 24F0. Well, that is the address of our temporary result object, right? Left-hand side has this address, 2490, right? Well, if we scroll up here, we can clearly see that is the address where F1 was originally allocated up here. So that makes sense because we said F1 equals the result of a sum operation, okay? So this whole operator runs, it makes its copies, does all of its stuff. As soon as that assignment is done, though, that temporary object that was returned by this overloaded operator, right, allocated and filled in up here, is deleted. It's thrown away. And in the destructor, I added a print statement in there that says, here's the array. This is the address of the array that I'm deleting in my destructor. And you can clearly see it ends in 5320, and that is this array right here. So in my plus operator, I allocate an array and fill it in as part of the object that I return by value. Then a copy of that is made by this assignment operator. Then the temporary value is immediately deleted. Okay, this seems a little bit wasteful, right? What if these array had thousands or millions or trillions of elements in it? We would allocate one here for the sole purpose of copying it from a temporary object to an already existing one so that we could delete the temporary one right away. This is very inefficient. Okay, it works though. Okay, obviously the F1 object has a copy of these things. You can clearly see that this P array address down here at 5350 is not the same as the one that gets deleted up here. So I didn't like somehow consume this miraculously. You'll find out there are zero miracles in software. If there are miracles, it means you shouldn't be using whatever features you're using. All right? All software is well behaved, well prescribed, well defined. Even if it's not well behaved, it's very specific. The code does what the code does. And if it's doing something you don't understand, you're not looking at the right place. All right? So the bottom line is nobody miraculously figured out how to just let this F1 somehow own this existing thing that was otherwise going to be wasted right away. Okay? You then see the, the F3, the F2, and the F1 objects go out of scope. And I talked about that before, okay? So this inefficiency in here is what we're talking about, okay? This aggregate thing. Foo is an aggregation of all these things inside it. One of those things, namely this array here, can be incredibly inefficient to copy. And that is especially annoying if I'm going to use an assignment operator like this and then throw away the thing I just copied like 10 nanoseconds later. Okay, so this is what we refer to. So now we're moving into what we want to call move semantics, all right? If you think about this for a minute, it would be nice if we could miraculously just kind of move this thing out of the foo here, this temporary foo, and then kind of adopt it over here by have F1 adopt the thing over here, rather than allocate it, fill it in, copy it, and then throw it away right away. We allocate it, fill it in, and then move it over to F1. And that's exactly what we're talking about. All right, so let's look at the differences between copy constructor version 9 we were just looking at and version 10 that we're going to look at next. So this diff shows you the only difference between these two files is I've added another overloaded operator. That's all we've done here. Everything else is 100% the same in every way. So let's look at this new function in the context of what's going on here, all right? So here's the assignment operator we were looking at before, and here's this new one. Look at the differences. The assignment operator we've been talking about so far, it returns a reference to what will be this, right? We talked about that when we were talking about overloaded operators. And it gets a right-hand side, a reference to the right-hand side that's a const. Look at this one down here. It returns the same thing, a reference to this, as we'll see in the end. Same operator equals, well, what's going on with this thing here? Okay. Regular overloaded assignment, const, reference to the right-hand side. This move assignment operator, and we're going to see this is going to go reach in there and steal that P array out. Instead of making a deep copy like it did, we just saw, I'm going to use this one and I'm going to steal it. And the way this thing works is you have two ampersands in here, and it is not a const. Okay? This thing here is called an Rvalue reference. Okay? And it is not a const. Therefore, if we want, we can reach over there and we can change it. All right, so that's the big thing here. If we're going to steal that P array from the thing on the right-hand side, we need to be able to modify the thing on the right-hand side when we remove it. Okay? This was added in C++ 11. This was not around for the first 20 years of C++. And a lot of people got upset because of exactly what we just saw. If you have a multi-megabyte thing in that object, then you have to avoid using overloaded operators and things like that, which are nice in some circumstances. And but, because of efficiency, people were not using them. So they provide us a way to pilfer the things out of the object on the right-hand side if we want. So let's see how that works. Once you've defined it like this is just a special way of defining a reference. Otherwise, it is just a reference. Okay, other than in this context right here, it's no different. It doesn't behave any different later on. We use this special context to let the compiler know that this is supposed to be an Rvalue reference instead of just a regular old reference. So here's our function here. I print out the usual thing. This is really the exact same as the other one, but in this case I changed this so we can recognize which one gets called. Okay? I do the same check. Am I going to assign this thing to myself? I don't want to do that. Okay? If the user said F1 equals F1, this will catch that and not do it. And we do the start out the same way. We copy the A and the B. We scroll up, we can see that's what we did before up there. Copy the A and the B. And rather than making a copy of the P array, we now do this. What do? Well, if we have one already, remember this is an assignment operator, not a constructor. This is an assignment. That means the thing on the left-hand side has already been constructed, and we need to update it. Therefore, it may very well have a P array in it already, and we'll see in this example, it does. Remember, we're going to execute F1 equals F2 plus F3 well after we've initialized and filled up F1 with a bunch of stuff. So we need to throw away whatever's in there now and make sure we clean it up and don't accidentally forget. And once we've done that, we can come along here and do what? Well, we need to say, remember, we're making a copy effectively. So the new array, the new array size is the same as the original one. Okay, just like I'm grabbing a copy of the A and the B, I'm going to grab a copy of however many elements there are supposed to be in P. And then I'm going to just point my object, the L value of this assignment operator, the thing on the left-hand side. The P is just going to point to the same place as the thing on the right-hand side. Remember, this addresses this one specific case where we know the thing on the right-hand side is going to be deleted right after this assignment has completed. So at this point in the code, both the one on the left-hand side of this assignment and the one on the right-hand side both point to the same array. Okay, they're both sharing the same thing. And we talked about that in the copy constructor when we talked about the pros and cons of deep copying, right? So we need to make sure that the object on the right-hand side of the equals knows that we stole that array away from it, okay? Now, this depends entirely. What you do down here is 100% dependent on your design of your object. In this particular case, what we're looking at here is the logic necessary to make sure that the destructor won't screw everything up, okay? Needless to make sure the destructor will work okay. And we'll go back up there and review that in a second. We say the right-hand side, the array pointer on the right-hand side, we're going to set it to null. That way the thing on the right no longer points to that existing array that we've grabbed and now are pointing to by the object on the left-hand side of the equal sign, right? Now, as I say down here, depending on how you design your object, you might actually have other things to do. Now, for consistency, you might want to set the number of elements in the P array to 0 for the object on the right-hand side here, okay? Because technically now it is 0, although I don't have to do this for this particular example, right? Why? Because that is not a concern in the destructor here. Remember, this is the thing on the right-hand side is going to be destructed the very next thing after the assignment is done. So look what happens in my destructor up here. If I don't set P to null on the thing on the right-hand side, then it deletes the thing on the right-hand side. That will cause that array to be deleted. Now think about that for a second. If I don't set it to null, on the object of the right-hand side of the assignment operator, then both the left hand and the right hand I'll be pointing to the same array at the same time. If then one of those, in this case the thing on the right, decides to delete it and pull the rug out from under the feet of the guy on the left-hand side of the assignment operator, we will have a problem, because the left-hand side is the thing that'll get used after this assignment is done, and it won't. At that point, when it decided to make a copy of the pointer to the array that's owned by the thing on the right-hand side, it'll be pointing at something that has been deleted and will break your code. So the point here is make sure that whatever you do when you steal things away from the right-hand side, that you let your own code, this is a message to your own destructor, that when it's called on the thing that's on the right-hand side, that it doesn't screw up everything, okay? So you need to kind of keep track and make sure that this is an agreement with the rest of the methods and stuff in your code. So this code did not change, as you saw in the diff. But let's look and see what's going on here. Just a quick review. We use the assignment operator up here, and then we use it again down here. These two are very different. When I say F2 equals F1 here, this F1 object is not going to be deleted right away. Therefore, this one will still call the existing assignment operator that we saw I didn't change. This one down here now has an option. The compiler knows that the temporary object returned by the overloaded plus that executes to do this expression here will be deleted. In fact, it'll be deleted before it even gets down here to print this line. Okay? And we saw that in the last output, and we'll see it again. Because of that, it can use our fancy schmancy move semantic assignment operator, which is this new one. Okay? So let's go ahead and compile up this version. I guess it's already compiled. Oops. All right, and let's see what's going on here. Scroll back up. From the top, everything up here is going to be the same as last time, so we don't really have to go over it again. We remember we created the F1 and we assigned it a value, and then we created a 2 and we assigned it a value by calling the overloaded assignment operator. And because I just said F1 does not get destructed right away, this is the exact same thing as it did last time. And this P here and this address and its copy is unique and different from the one that's in F1. This ending in 52E0 is definitely a different address than the one that ends in 52C0. All right. Now is when we see some interesting things happening. So we create the F3. There's no difference there. We begin our addition. The addition does the exact same thing it did last time. No changes there. It creates a new temporary that's at 2F60 and fills it in just like I told you about last time. And that is the object that is returned by value to the assignment operator. And look what's going on here. Because the compiler knows that the temporary object at address that ends in 2F60, which is this one here, the result from the overloaded plus, because it's going to get deleted right after this assignment, the compiler looks around to see if you have provided this optimized move assignment operator, and it will use that in preference to the regular assignment, like it did up here, so that you can optimize this moving. Now let's look closely at what's going on here. The right-hand side of the assignment operator and the left-hand side, thing on the left is the address of our F1 object. You can see that right down here when I print it out again. The thing on the right that ends in 2F60 is the address of this temporary object that's returned from the plus. So far, so good, same as last time. However, when this thing runs, remember, it steals this array away from the thing on the right-hand side. Look at the address here. It ends in 5320. When I am done with this move assignment operator, look at this. I stole that array, whose address ends in 5320, away from this temporary object rather than copying it. And you can also see that the destructor in this case, when it says I'm going to delete my P array, there's a 0 in there. Last time we ran it, it had the array of the P array in there. So this says I have nothing to delete because, as you recall, when we did the move assignment operator, we set it to null pointer. The value of null pointer is, in fact, 0, the address of 0. Okay, so when we dump out F1, we see again, we have made copies of these items, and those are easy and cheap to copy, and we stole this big array. Again, this could be multi-millions of things, and that saves you a lot of time. This alone could, have earth-shattering improvements in performance of your code, so that those of us that are impatient and don't like to wait forever when we use our software can write software that runs faster than it otherwise would if we did not have the ability to move members of aggregate objects around rather than making copies of them unnecessarily. So that's how Rvalue references are used in what we call a move assignment operator on aggregate objects that are more complex than just having simple, trivial member variables. This entire subject is what you generally hear referred to as move semantics. Thanks for watching. See you next time.